This morning, and the last speaker of the workshop is Julia Brandes, and she will speak about rational lines on cubic hypersurfaces. The title is over there. Okay.
Yes. Well, thank you to the organizers for giving me the opportunity to speak here, and also thanks very much to Hugh and Antoine for giving me the opportunity to speak now instead of yesterday afternoon. Yesterday afternoon wasn't good. So, rational lines on cubic hypersurfaces. I've talked about this a few times already, and so has Rainer. So apologies to the non-empty set in the audience who've seen this already. Well, let f be a cubic polynomial, homogeneous, well, let's just say polynomial for the beginning. And I'll call the hypersurface I'll call that curly V. And then, of course, the question is, does V contain rational points? And of course, there've been several talks mentioning Hasse or local global principles. So, well, the rationals sit inside the reals and all the p-adics, and we say the Hasse principle holds. If real and p-adic solubility implies rational solubility. And as you're all aware, it's not true in general, and there's lots of research on abstractions. That's not something I'll be talking about today. But one positive result when the Hasse principle holds is, of course, Birch's theorem. So if we have the homogeneous, well, the form as above, then and we'll assume that it's non-singular and of degree D. Then the Hasse principle holds for the hypersurface for the associated hypersurface if the number of variables is at least 2 to the d times d minus 1. If d is 3, you can compute that, you get 16. And in fact, more is true. That essentially comes out of that proof. out of that proof, you just need to write it down. So I'll just write down, I think the first person to write it down was Christopher Skinner, but I'll write folklore because it was known before. And that's that under the conditions of Birch's theorem, we actually have weak approximation. So we know that the rational points lie dense inside the real points, and likewise in the p-adic points for each. So yeah, and this is weak approximation. Yeah. So we've got a Hasse principle. So all we still need is real and p-adic solubility. And what do we know there? Well, we know that we always have real solutions if the degree is odd. And in the p-adic case, well, that's a bit harder. So in full generality, we get that if the number of variables grows at least doubly exponential in the degree. That's Wooley in 98. Of course, if we have special cases, special degrees, we can do better. If we only look at all sufficiently large primes, we can do better. For the Hasse principle, unfortunately, we need all primes, but yeah. So I'll say can do better. On the other hand, there's also counterexamples to p-adic solubility where the number of variables grows exponentially in the degree. So there's probably some leeway to be had, but we're not going to get anything polynomial. Not in this generality, at least. So under such conditions, we then get that by Birch's theorem that there are points. Of course, I had the word cubic in the title. So let's see what we know in the cubic case. So for cubic forms, we know quite a bit more. So let's just record Birch required 16 or 17, strictly speaking. But Wooley has done quite a lot of work on cubic forms. So in 89, he showed that if the form is non-singular, the Hasse principle holds if in as few as 9 variables, which is better than Birch. And, well, Heath-Brown before showed 10 in 83, if I'm not mistaken. And then Wooley, that's the best known in this generality. And then if you are willing to believe a few extra hypotheses, then you even get it for n at least 8. And that's under, well, some hypotheses. Yeah, so he has several L functions to behave well. Now that's interesting because, of course, for p-adic solubility, we need at least 10 variables. Which is sharp. So these with 9 and 8, that's a genuine Hasse principle, not just proving the Hasse principle by showing that they're actual points, but there's actual some p-adic, yeah. And well, if f is general, so if f is general, as in we don't make any assumptions about non-singularity, then we know that 14 variables suffice. So yeah, so as I said, in the cubic case, quite a lot of is known. So one may for the Hasse principle, and for existence actually, because the p-adic and the real conditions are satisfied. So we get existence, which thereby proves the Hasse principle. So yeah, so as I said, in the cubic case, we actually know quite a lot more than in the general case as well. So one question that one can ask is, given that we know quite a lot about under what conditions there are points, can we say something about how those points are distributed? So do we have rational lines, or one could ask for other kinds of objects as well, but I'll look for lines. So yeah, so that was the corner that I was warned about. Okay. Yeah, so that is a question. And that question has been studied, and yeah, one theorem that I'll quote here. That's been revisited later by Dietmann and Wooley, but they didn't improve on that particular statement, but I'll just state it anyway. And what they show is that let F be a cubic form. And assume that we have at least 37 variables. Then the associated hypersurface contains a line. And, well, the idea of the proof well, first step is you find one point. Which we can do because we have more than 14 variables. So that's good. And now we need to find another point. Such that, well, we need to find another point with a property that the entire line vanishes. So, well, we can, it's a polynomial, we can expand that. And in order to write down what that is, this notation, so let phi of x at 1, x2, x3 be the symmetric trilinear form associated with f. So that in particular we have phi of xxx is f of x. And so then we can write this f as phi of 3 times the same thing and use linearity. And what we get is that this is equal to s cubed f of x plus 3s squared t So we can write it like that. Now the first term is 0 because we picked x like that. And then this one is a linear form. And y, this one is quadratic. And we've got our cubic left. And, well, so the second step is then we restrict to the hyperplane defined by the linear form. So it's going to cost one variable, but that's okay. And the third step is we find a large linear space on the quadratic. And we'll try to find that space so that it does not contain our original point. Just only so that when we solve the cubic on the linear space, we don't accidentally find the same point again, because twice the same point does not span much of a linear space, or a line even. So such that Qx vanishes on W. And the fourth step would then be to restrict the cubic to that linear space and solve. So that's just the idea of the proof. It's a bit more complicated than that. But so you need sufficiently many variables here to solve that, then you need sufficiently many variables to find the quadratic space on here, the linear space on there, and but if you do it all, you get 37. Now, of course, that happened 20 years ago, and the world has moved on since then. And in particular, there's one theorem and so what well, Tim up there and Rainer and Heath Brown. And what they show is if you have a cubic form in at least 29 variables and a quadratic form with rank at least 28, then the intersection of the two underlying hypersurfaces satisfies the Hasse principle. And also, one can show that we always have p-adic solutions. So we'll get we'll get rational solutions if and only if we have real solutions. Of course, the real solution is an actual thing because we have a quadratic which might be definite. So, why don't we try to do this differently? Why don't we try to, well, fix our x, intersect by this, and then solve these two simultaneously? So, the plan is first first step is, well, first and second step is before, is the same as before. Find x as a rational point. Second step, restrict to the hyperplane. Now for the third step, well, we still need to make sure that we don't accidentally find the same point x again. So we restrict with another hyperplane that doesn't contain x. Apart from that, we're free how to choose it. So restrict to generic not containing x. And then the fourth step is solve f of y equals q x of y 0 on. I'm abusing notation a bit here, and I'm calling the hyperplane Lx. But, so that's a plan. So of course, when we want to do this, we'll need to make sure that we satisfy the conditions of that theorem. So, well, so what do we need? Well, the first part is we need f restricted to Lx. M is smooth. And at least 29 variables. And the quadratic, well, restriction of the quadratic has rank at least 28. And then the more interesting part is we need a real point. Well, for the first part, well, let's assume that we start with 31 variables. We Ah, right, yes. Very good, thank you. So, let's start by assuming that we have a non-singular form in 31 variables. We're going to restrict to Lx. Now, for generic, well, in the generic case, we would still be non-singular. Now, of course, this is a tangent plane, so we're actually going to pick up some isolated singularities. So it's handy that we've got the form, that we've got M as well. So if we choose M not too unfortunate, then we get something non-singular back. And for the quadratic form, it's really the same thing. So the matrix so if you look at what that form actually is, you see that it's just the Hessian of f in x. That's generically non-singular, so the same argument works. Well, we even have some space there because the same argument shows 29 and we've got some space.
Generically here means as x varies?
Yeah, as x varies over points in the hyperplane, hypersurface. Yes. So for B, I mean, A wasn't so hard, right? B is more interesting. So the part that's not hard to show is if Qx has so if the matrix, I guess I'm still abusing notation here, so Qx means the form, the matrix, and the hypersurface. Sorry. But I guess it's clear from context. So if we have at least 4 eigenvalues of every sign, then we can intersect with the 2 hyperplanes, and we're still going to have 2 of every sign at least. And this is crude. Then Qx and, well, then if you write it down, then without loss of generality, then you get this kind of structure, and you clearly get a real line on that. And if we have a real line, we can solve the cubic, and we get a real point. So f restricted to L has a real point. So we need to show that Qx has the right number of eigenvalues, of well, positive and negative eigenvalues. Of course, the eigenvalues of Qx depend on the x we started with. But now let's observe. Well, suppose the x we picked is a bad one. So let's suppose it's as bad as it can be. Qx is positive definite. Well then, if x lies on the hypersurface, then minus x also does, because it's homogeneous. And q minus x will then be negative definite, because this varies linear in x, because that's how the trilinear form, it's a trilinear form, there's two y's and one x in there, so it varies linear with x. So if qx is positive definite, then q minus x is negative definite. So if we have a positive definite point and a negative definite point, can't we kind of trace a path between x and minus x, so that somewhere along the path we get a good signature? So, well, does such a path exist? Well, it would be unfortunate if x and minus x were in different connected components. So do we have a connected component that contains both x and minus x? And one lemma is that, yes, there is such a connected component. Well, it definitely works for smooth, probably also for non-smooth. Well, so, yeah, if you think projectively, then one can show that there's at least one-sided connected component. Somehow, because of the pluses and minuses, I prefer to think in terms of the unit sphere, which is kind of like the projective space, except we don't mod out by plus and minus. So, or perhaps R plus maintains. So in that language, there is a connected then we can write down that. So if we choose our x in that connected component U, then we find the path. Now, another thing that could happen is, so the eigenvalues vary linearly, or in particular continuously with x. So one thing that could happen is perhaps they're all positive at the beginning, and then one after the other they get negative. If they all get negative at the same time, that would be unfortunate, because then we might go from positive definite straight to negative definite, or to almost negative definite. So that would be bad. So there's another lemma. Probably should have credited this one as well, just I forgot. So suppose we have a non-singular cubic form with Hessian hx and x, then the points in affine space where the rank of the Hessian is small has small dimension, which of course we would assume. So what does that mean? Well, that means that points where the rank is smaller than n minus 3, well, they have codimensions 3 in and so if we look at the points on the hypersurface, I mean, I'm really sloppy here, but there is lots of space, so I can afford to be sloppy. So well, those on V have codimension at least 2 in V. Now if we have codimension 2, that means we can walk around them with a path. Yeah. Such that we have, well, rank at least n minus 2 everywhere. And by the same argument, we also get again, this is sloppy. One can probably, well, one can do better. I'm sure one can do better, just we didn't bother to because there was this one variable of space because we needed the rank of the cubic to be only 28 and not 29. So we can choose that path. And of course, along that path, at most 2 eigenvalues change sign simultaneously. So we definitely find somewhere between what did we need, at least for positive and for negative, and we have 31 variables. So we definitely find some signature somewhere. So we clearly get a good So I'll just state the revised plan and then I'll state the theorem. And then what is, and then it's 12. So we find a rational point on our connected variety that is that reflects, and if it's sufficiently indefinite, that's good. If not, we find the path such that, well, these two are satisfied for that point, x naught. And, well, now we just found some point, and we were doing a real argument. That point we found need not be rational. But by weak approximation, we can find a point that's closer to x naught than the nearest bad point. So by with x minus x naught less than half distance to the nearest bad point, which means x is also a good point. And then next we intersect with our Lx and our generic M. So, well, the condition A is satisfied. And, well, for x we only assumed n minus 1. So we have rank Qx restricted to L m n minus 3 because we intersected by 2 hyperplanes. And then number 4 is apply theorem A, which we now can do, provided that n is at least 31. Because then we've got 29 variables non-singular here and at least rank 28. So was on the archive last year. So let F be a non-singular cubic form in at least 31 variables, then V contains a rational line. And yeah. That's better than what Wooley did, but we need smoothness and he didn't. But yeah. Yeah, so that's that from me.
Okay, let's thank Julia for this nice talk and classical mathematics. Any questions or comments or remarks? Yes.
Is there a reasonable conjecture about the minimum number that you should get here instead of 31?
I do not know. Well, the best counterexample we came up with was 11.
Ah, okay, so that was my question.
Yes.
Actually. Thank you.
Other questions or comments? I want to ask you, you said weak approximation. Do you mean you just can approximate for every p, EQP, and for the reals, or you can approximate at finitely many times? I mean, the rational points. So in your
Actually, I mean only R in my case. I don't need the primes.
So, but if
But
somebody
infinitely many
tells you,
places is enough.
yeah, but if somebody tells you what I want, actually, the coefficients are to approximate something, a line in over the periodics, a given line over. So, can you do that?
Wait, can I do what?
So, what these people want is actually more than a weak approximation. Weak approximation, in your sense, was that the rational, I think, in the initial theorem,
The rational points lie
Yes.
dense.
in the reals and in the periodics for every
separately.
p separately. Now, if I give you finitely many p prime numbers and maybe the infinite place, are there rational points which approximate given points then? Not separately, but at these finitely many primes?
Finitely many, yes.
Okay.
Yes.
So that's-
Infinitely many is a different matter, but
yeah,
finitely
no,
many, yes.
That doesn't. Okay, any other remarks or comments?
Simon,
So it
behind
seems-
you.
Oh, yes.
Yeah, so in some comparable situations, it can even be an advantage to be singular because it restricts the geometry of the variety in some way, which is useful for the proof. So there are many different points in this proof where you used non-singularity.
Yes.
Have you studied which of these it might be actually helpful to be singular? If that makes sense?
Not that specifically, but yeah, I was just thinking about one of those questions, but yeah, well, I mean, as you said, we use non-singularity in many different places, and in some of them, you can get away with, well, more or less without non-singularity or with something weaker than that. But I mean, the most tricky part seems to be to make sure that if you want to play this kind of argument, that not all your eigenvalues change sign at the same place. So that part.
Okay. Yeah. Thank you.
Okay, now I look around. So it seems so. Let's thank Julia again for the nice talk. And before we go, before we go,
As the last speaker, I'd also like to thank the organizers for organizing a wonderful conference. And the speakers for giving lots of good talks. And the very nice audience, of course.